when he was young, he was a sickly kid, and he was used to staying in bed a lot, sleeping late. Well, he was born to a wealthy enough family that he could continue those habits into adulthood. I think he became a soldier, if I remember the story right, at some point. But he liked to sleep in bed late whenever he could, and because he got a lot of thinking done. And one day he saw a fly crawling on a wall. He had this brilliant inspiration. He thought, I can describe where that fly is. So he said, let's take a number line or a scale, and we'll run it horizontally. And by then they had negative numbers. And then we'll put another scale on it that runs vertically. And you get the idea. I usually don't fill in all those numbers. I don't think it's that necessary, but I did this time. And as it evolved, we call this the x-axis and this the y-axis. It says, okay, here's how we're going to determine the position on this plane. For example, this position right here will be 3, 2. And we write that in parentheses. That's called an ordered pair. And it means that to go 3 horizontal and 2 vertical. Horizontal, vertical, x, y. Always that order. Always that specific order. 3, 2. If I reverse the 3 and the 2, I get a different point. 2, 3 would be up here, which would be 2 horizontal and 3 vertical. There you go. Something on the axis, for example, down here, on the y-axis, the x value is 0, and the y value is -4. All right, well, that's the idea. And Descartes quickly found that he could represent geometric shapes with algebra. And algebra shapes had geometrical representations. For example, if you connect these two dots to form a line, I guess I'll do that in green, we'll get this line. Okay, and it turns out that this line can be represented by y equals to, let's see, what would it be? It would be x plus 5. Nope, 5 minus x. Sorry about that. We would probably write it as -x plus 5. Okay. You could also rewrite it as x plus y equals to 5. And sure enough, you can see these 2 points, 2 and 3, if you plug them in here, 2 plus 3 is 5. Put 3 and 2 in here, 3 plus 2 is 5. But there are a lot of other numbers that would work. 1 and 4. How about 1,000 and -995? That would work. You could also go to fractions and decimals anywhere you want. As it turns out, that this algebra equation, it can be shown that it represents every single point on a straight line. All infinitely many points on a straight line. So something that textbooks tend to take for granted. I actually proved it to myself one time that's actually true. And it's not that hard to do, but anyway, I think it's important to think about those things, not take everything for granted. Well, in any event, here we have it. So a very simple example where an algebra equation represents a geometry object, or you could think a geometry object can be represented by an algebra equation. I can't tell you how important that was. Descartes, I think, published his analytic geometry book in 1642, and so he called this analytic geometry. This is the blending of algebra and geometry. And shortly afterwards, Isaac Newton and a German, Wilhelm Leibniz, both independently discovered calculus. And after we had calculus, then the scientists could come in and start applying it to science and engineering. And that really enabled the technology that we enjoy today. We would not be in this technological era without the XY plane. So, although it looks pretty sterile in a textbook, this has to be ranked as one of the top achievements or breakthroughs in human thought in history, because it led to calculus and all the subjects above it. It led to breakthroughs in science and engineering and technology. So many things we take for granted, for example, this video, would be totally impossible without this sort of understanding between algebra and geometry. So there you go. Well, that's our understanding of it, and then from here we'll move on to the more mundane aspects of graphing.